All right, so in the last class, I mentioned that we're going to be dealing with sampling distributions, right, which was the probability distribution of a statistic. We mentioned 4 sampling distributions, the standard normal distribution, which we're all familiar with, and then 3 distributions which we're not that familiar with, the student's t distribution, the chi, etc. squared distribution, and the f distribution. So what I'd like to do today is introduce the remaining 3 distributions, and hopefully after the break, we can look at some applications of those 3 distributions. So let's start today's class with the student's t distribution. Why is it called, keeps focusing. Why is it called student's t distribution? The statistician who developed this distribution, William C. Gosset, he published his work under a pseudonym, and his pseudonym was Student. So because he was known as Student, then this is called student's t distribution. Let's suppose that we have a random sample. And remember that a random sample consists of the probability distributions of all of the different runs of the experiments in a successive repetition of experiments. So for example, we have an experiment, we run it once. The probability distribution of those outcomes, we can call it x1. And x1 has all of its outcomes and associated probabilities. We talked about this in the last class. We have another run of the experiment, which will have outcomes with a probability distribution that we'll call x2. Now remember, because each run of the experiment is independent of each other, and because each experiment, we assume that we run it in the same fashion, the probability distribution at x1 will be the same as the probability distribution at x2, which means that both of these samples will have the same outcomes with the same probabilities for each outcome. I have a question. We have 2 samples. Each of them has the same number of outcomes, or the same types of outcomes, same values for outcomes, and the same probabilities for each outcome. Does that mean that they will both have the same outcome? No, right? You can have different outcomes, and that's where the variability comes into play. If you're not able to visualize this, then think of, again, rolling the die. Your first time rolling the die, probability distribution where each number has a 1 in 6 chance of being rolled. The second time you roll the die, you have the same probability distribution where each number has a 1 in 6 chance of being rolled. But just because they both have the same probability distribution doesn't mean that they will both have the same outcome. I mean, they may, but they also may not. So let's say we have n samples. So we run this experiment n times, and for those n times, we are going to have n probability distributions. We can define a random variable t. This is a name that I'm giving you. Just define a random variable t as the mean, or the statistical mean, so the mean of the sampling distributions, so the mean of all of these values, minus the mean of the population. Remember, each one of these variables has its own mean and standard deviation and variance associated with it. Now, of course, we know that since each one of these samples has the same probability distribution, they will all have the same mean. So what I'm doing here is I'm taking the mean of the sample. So I take all of these, figure out what the mean was of all the outcomes, and subtract from that the mean of the population. In other words, the mean of each individual run in a sample. And then I divide it by the sample standard deviation over root n, where n is just the number of runs in your experiment. Then I've created a random variable. You may recognize this a little bit from last class. In the last class, we mentioned that our normal distribution would have something very similar, except that we'd be dealing with the standard deviation of the population. Here, I'm looking at the sample standard deviation. Does anybody remember what the difference was between a sample standard deviation and a standard deviation? It's the same difference as the sample mean and the mean. Any ideas? So let's start with the standard deviation, right? How did we calculate the standard deviation? It was the square root of the variance. And how did we calculate the variance? We needed what? Christian says the mean, that's right, we need the mean. And in order to calculate the variance, we would have to, we would have to use or see the difference between individual value in your probability distribution and the mean of the probability distribution. We would square that, and then we would multiply by the probability of each individual value, and that was your variance. However, when we talk about the sample variance, instead of using the mean, we would use the sample mean, right? And because sampling statistics don't really have probabilities associated with them, then we would just add them all up and then divide by n, or n minus 1, I think, for the sample variance. So the difference between this random variable and that standard normal random variable that I defined in the last class is that this random variable doesn't use the standard deviation, it uses the sample standard deviation, which of course has to do with what values you recorded, not really with what is the probability distribution. If you need a bit of a recap on that, just go back to when we talked about organizing data. Those were the modules where we discussed the sample mean, the sample variance, and the sample standard deviation. Now, student, or William Seeley Gossett, found that this random variable is going to have a probability distribution, which he coined, or he named, the T distribution. So if I take this random variable, and I find the probability density function of that random variable, we'll see that that probability distribution follows, or is, the following. Here's where that little summary table will be helpful. We'll have the gamma function of k plus 1 over 2, and I'm going to define what k is in a second. Divided by square root pi k times the gamma function of k over 2. All of this is then multiplied by 1 over x squared over k. It's a really long equation, as you can see, plus 1, elevated to the power of k plus 1 over 2. So this is the probability density function of this random variable t, which means that if you know, right, if you know the variable or the outcome, which is x, you can find the probability density function for that outcome by plugging in x into this equation. We've already talked about the gamma function. It's a function, so as long as you know what it is you have to plug into that function, you can find it. But there is a variable here that we haven't defined yet, and that is k. Now for this distribution, k is defined as the number of degrees of freedom. And we will explain what degrees of freedom means when we start talking about applications. But how this relates to our sample is that our sample has n minus 1 degrees of freedom. Therefore, k will be equal to n minus 1. So if you have a sample with 20 observations, that means that you will have 20 minus 1, 19 degrees of freedom. And as long as you know this, the number of observations, notice that all you need to do is plug in the value, the outcome that you're trying to find, and you will be able to get the probability density function for that value. This also means that you can plot it. You can plot this distribution in order to analyze it a little bit graphically. The measures for this distribution, so if I take this distribution and I find the mean, the different measures, the mean will be 0, which is pretty interesting, right? The measures will be 0. And the standard deviation, or my apologies, the variance of this distribution is going to be k over k minus 2. We're not going to do the whole math here because it'll take forever. But if you find the mean of this probability density function and the variance, you will get that the mean is 0 and the variance is k over 2. Now notice that in order for us to have this type of variable, okay, we need to have multiple observations. Right? Because if you look at the variance, you see that the variance is only exists when k is greater than 2. Because if k were 2, that's an undefined variance. If k were less than 2, then we have a negative variance, which that doesn't make sense, right? Because variance is a squared value and it's positive by definition. So what this tells me is that this random variable t can only exist if you have more than 2 observations, which is why I did x1, x2, all the way to xn. So it can be 3, 4, 5, but never 2 or less than 2. So this is what we call the student's t-distribution. You can see in your book what it looks like. I didn't think of putting it or bringing in a figure for today, but you can see what it looks like in the book. And you'll see that for different degrees of freedom, so for different values of k, the distribution will start to change. Now the shape of the distribution, or the exact shape of the distribution doesn't really matter. However, there are some aspects of the shape of the distribution that matters. The student's t-distribution, if you plot it, is going to be symmetric. That means that to the left of the mean and to the right of the mean, you will have pretty much the same distribution. It actually looks very similar to a bell curve, the normal distribution. However, for smaller values of k, for smaller degrees of freedom, that bell curve will have thicker tails. In other words, it's going to look a little bit flatter than the bell curve. Now you'll notice that if you increase the values of k, and here's where something like decimals would be good to use, which I didn't think about until now, but too late. If you were to plot this and you start increasing the value of k, you'll notice that your student's t-distribution is going to start looking more and more like a bell curve. In fact, if your k tends towards infinity, so you have infinite degrees of freedom, then the student's t-distribution becomes a bell curve, becomes a normal distribution. So at the limit of k equaling infinity, the student's t-distribution becomes like a normal distribution. It converges towards a bell curve. That's the student's t-distribution. Like I said, we're going to look at applications at the end of this class or later in this class. But at least I wanted to introduce the main things you need to know about the distribution. And those main things are that it's symmetric and looks similar to a bell curve. Just a little bit flatter than the bell curve with thicker tails. However, as you increase your k value, as you increase your degrees of freedom, and notice that your degrees of freedom depend on the number of samples. So as you increase your number of samples, such that you have infinite number of samples, then your student's t-distribution will end up looking like a normal curve. Now this is actually in line with what we said last time in class. Last time I mentioned that if you take multiple samples, regardless of what distribution each individual sample has, but if you take an infinite number of samples, then that probability distribution ends up looking like a normal distribution. And this is what the student's t shows us, albeit in a more mathematical sense. Okay? So that was the student's t distribution. Now let's talk about the chi-squared, Gsquared, Chisquared distribution. To avoid having to use all the orthodox and unorthodox pronunciations, I'll just call it the Chisquared distribution, which is the worst pronunciation, but let's just use that. Once again, this is where your summary table of probability distributions may come in handy. Again, let's say that you have your sample, your random sample of n observations. These observations all share the same mean and all share the same variance. We can create a random variable. I'm going to call this random variable capital X. Technically, it's capital G, right? But it looks like capital X. Maybe I'll use this to distinguish it from capital X. We create a random variable, capital E, squared. And I'm going to define that random variable as n minus 1 times the sample variance of this random sample divided by the variance of this random sample. If I set this variable, this G-squared variable, capital G-squared, then I have what's called a Chisquared distribution, which means that the probability distribution, I can calculate the probability distribution for this random variable. It's going to look like this. It's also a somewhat complicated equation, so bear with me. So we'll have 1 over 2 elevated to the power of k over 2 times the gamma function of k over 2. And all this multiplied by x to the power of k over 2 minus 1. And multiplied by e to the power of negative x over 2. So I guess divided by e to the power of x over 2, but it's okay. Now this distribution exists for x greater than 0. Which means that your values, right, should not really be less than 0, greater than 0. This is called a Chisquared distribution. Just like with the student's t distribution, A represents the number of degrees of freedom, and in this case, k is also going to be equal to n minus 1, meaning that this probability distribution will have n minus 1 degrees of freedom. If I were to calculate the measures of this distribution, the mean will be k, and the variance will be 2 times k. Remember, these are the measures for the PDF, okay, not for the individual populations. This Chisquared distribution is called Chisquared because it's the Greek letter P. And you can see that it's somewhat complicated compared, just like the student's t distribution. This one will not be symmetric. In fact, it's going to be skewed. You can look at different values and different examples of the Chisquared distribution in the book. However, I do have some good news. The t distribution and the Chisquared distribution are so commonly used that you don't actually have to calculate this for every x value. What you can do is look at tables called the t-tables or the Chisquared table, which will include, just like with the standard normal table, they will include values corresponding to the percentages of these distributions. Now, the standard normal table, all you need is your value, I guess your value of z, so you can get your z-score, where the z-score is just a percentage, probability. In this case, you have two variables. Not only do you need your value, your Gsquared value, you also need k, the number of degrees of freedom, in order to get the corresponding probability for those values. There's a bit that I want to talk about related to how those tables work. But I think instead of trying to explain it, I think it would be better if we work on some examples and working through those examples, then we can try to explain how the tables work. Because the tables are, even though they look similar to the standard normal tables, they're interpreted a little bit differently. And that different interpretation has to do with the fact that one of these probability distributions is symmetric and the other probability distribution is not. So let's leave the interpretation of the tables for later today. The third probability distribution that I'd like to talk about today is called the F distribution. We've already covered students T, G squared. Now we're looking at F. The F distribution is an extension of the Gsquared distribution. In this case, let's define two independent chi-squared random variables. Can't really call them chi-squared because I want to distinguish the two. So I'm going to call my random variables W and Y. And let's say that W has U degrees of freedom. So K for W is equal to U. And let's say that Y has V degrees of freedom. So that K for my Y variable is V. I can take these two independent chi-squared random variables and create a probability distribution that is based on the ratio of the two. So I'm going to define a random variable F to be equal to W divided by U over Y divided by V. If I were to find the probability density function of this distribution, I would have the following. So it's a little bit more complicated. So once again, bear with me. In the denominator, I'll have the gamma function of U over 2 times the gamma function of V over 2 times U over V multiplied by X plus 1, elevated to the power of U plus V over 2, or simply the average of U and V. In the numerator, I'll have the gamma function of U plus V over 2 times U over V, elevated to the power of U over 2, times X to the power of U over 2 minus 1. This is the probability density function for the F distribution, and it exists for X greater than 0. Why? Because remember, chi-squared variables, by definition, have to be greater than 0. And because F depends on two chi-squared variables, then it will also have to be greater than 0. This is the F distribution. As you can see, a far more complicated one to model. And we usually write it in notation. So normally if we want to talk about an F variable, we typically write it as F of U and V. This is our notation for the F distribution, where U are the degrees of freedom for our first chi-squared variable, and V are the degrees of freedom for our second chi-squared variable. The measures are as follows. The mean is equal to V over V over 2, or let me rephrase, V over V minus 2. And notice that this tells me that there have to be more than 2 degrees of freedom. But remember, the degrees of freedom were equal to n minus 1. So if there have to be more than 2 degrees of freedom, and n minus 1 will also be the degrees of freedom, that means that there has to be more than 3 observations, more than 3 samples. It's a little bit more restrictive. Let's add some more restrictions. The variance for the F distribution is going to be equal to 2b squared multiplied by u plus b minus 2 divided by u b minus 2 elevated to the power of 2 multiplied by b minus 4. Now you can see that this actually adds one more restriction. B cannot be 4 or less than 4, which means that B has to be greater than 4. B are the degrees of freedom. Therefore, for our second chi-squared variable, we will have to have at least 5 observations, right? And remember, degrees of freedom are n minus 1, and that's 4, which means that n has to be 5 or more. Okay?
Is that ZB minus 8?
No, it should be a 2. Okay. So that is the F distribution. It's all I know. It's definitely more complicated than the other probability distributions we looked at, which again is why the table is a helpful instrument to use. Just throwing these equations at you doesn't really help out unless you know why or how to use them. So now that we've wrapped up our conversation on parameter estimation, let's start a new conversation on confidence intervals.